food.
As long as there's a grade in the grade book, not a zero. I'll double check.
I just didn't write it down.
Yep. Question about the radioactivity homework. Is there a answer key or?
Can you,
Yeah.
do you know what week that is by any chance? Sorry. Was that 8?
Sorry, I'm moving.
I know, I'm also looking.
I don't remember.
No, it's not 8. Let me try 7. I think it's week 7.
Yes. So in her calculations on page 3, number 6.
How long will it take a radioactive isotope to decay to 1/10 of its original mass?
Yeah, so her calculations have 0.5 to the x power. So she has m over m, like m initial. And so m over m initial equals 1 over 10, which equals 0.1. And she sets that equal to 0.5 times, or 0.5 to the x power.
Yeah, I'm looking at where you're looking.
Where did the 0.5 come from?
I'm not quite sure. All right, let's look at that problem. I'll probably have to pull up the radioactivity notes. So we're looking at the week 7 homework, a question. So how long for radioactive isotope to decay to 1/10 of original mass, and we're given half-life 3.75 minutes. All right, so I'm not going to look at Dorothy's answer, but let's pull up. I have to pull up my equations at least. Where's my cheat sheet? There we go. So looking at this, right, so we care about probably these two equations. And so we're given T half-life, so the first thing I would do is let's plug in for our K, given our T half-life, and then we can use this form. So time half-life is equal to 0.693 over K. So then we have 3.75. Now this is minutes, so just be consistent in your units. And so what does that give us for K then? Let me pull up my calculator. You said 0.184? Well, then it should be like 5, right? Oh, because when you do, so 0.693 divided by this, that gives you 1 over K.
So I multiplied K on both sides, and then I divided 0.693, and I divided both sides by 0.75.
So times K. Oh, I think I did it wrong, sorry. I should have done 3.75 divided by 0.693. Oh, man. Sorry, flub time. Let's try one more time. 0.693. And then I should have inverted my answer. Okay, now we get the same answer. Sorry. So now we both agree. So K is 0.1848. Again, I'm not sure where Dorothy got her equation. She could have used a little math trick that I'm just not seeing. But then I would just plug in, so finding time now, using this equation, and then we can just do the 1/10. So we could still use the ln of 0.1 since we want 10%. And so natural log of A at time over A naught is equal to negative KT. And so our time will be in minutes. So this gives us natural log of 0.1 is equal to negative 0.1848 T. And so we at least get the same answer as the answer key, but unfortunately I don't really know what she did for her math trick. I don't know if I was helpful or not.
I'm just curious about where the 0.5 came from, because I couldn't find it in the.
Yeah, I'm wondering if she said something like 0.5 would be like your half-life, and then X would give you how many half-lives, and that's how she solved it. That'd be my guess, but yeah. I feel more comfortable personally just like following the formulas. That's just my take on it, but either way you get the same answer if you do a fancy trick. Yeah, because she determined how many half-lives were present first, whereas we just skipped that and just went to our time with the rate. So yeah, that's what she did. But to me, that's not as intuitive, but that's, again, that's just me personally, and I like equations and plugging stuff in. But if the way on the key makes sense, you know, go for it. While we are talking about questions, let's go over your quiz, because I made a little oopsie on it, so I wanted to go over what I messed up and what I was kind of looking for. And I have your quizzes if you didn't get it back. But the one that I made a mistake on was number 2. So it asked how many unpaired electrons in, and this is where I made the typo. So it should have been ruthenium cobalt 6, but I put a 4 there by a typo, so it made the problem a lot more challenging. But by the time I realized this, y'all were already in the middle of it, and I thought, well, we'll just see how the answers go. And so I was pretty generous because I was, you know, again, just kind of looking for thought process with this. So I'll go over kind of what I was trying to get at, and then kind of the range of acceptable answers and how you could have approached the more difficult problem. So the first thing you had to establish was how many d electrons it had, and that wasn't changed by my oopsie. So how many d electrons does ruthenium 2+ have? 6. So D6, so that was a good portion. So that's what I was looking for, but again, if you got different answers, I try to be generous. And so what it was supposed to be, so I'll put correct if I had not made a typo. And some people still kind of went with this, which I kind of expected because we only went over really octahedral. And so what I was looking for is if I had not made the typo, you would have this octahedral splitting diagram. So remember, octahedral is different in that it has 3 on bottom and 2 on top, and those are the anti-bonding. And so this was a strong field ligand, so ideally you would have done a low spin compound, and it would have no unpaired electrons. So that's kind of what I was looking for, or at least, again, without a typo. But then with the typo, and people were clever, and so saw, well, it's 4, and the only other one that we had talked about was a tetrahedral splitting diagram. And so this is kind of tricky too, and I don't want to get too into it, but there's like 2 tetrahedral forms. So, you know, we talked about the tetrahedral one, but there's also square planar. So that's why this one didn't quite work out too well. And then I was just, again, looking for thought process. So if you had recognized, especially that this was a strong field ligand, then you would have gone 1, 2, 3, 4, except 5, 6, and that would have given you no answer. So that might have confused people. But I was also okay if you had done something, you know, like this. I still accepted it, just as long as you explain and, you know, showed the diagram, showed 4 unpaired electrons. Yeah. So that goes back to the spectrochemical series, and I don't really expect y'all to know that for our purposes. So my questions would be more like, how do you identify it? Kind of like the last question, which is what I was really looking for, is like, do you know whether it's diamagnetic or paramagnetic? Because that's the only thing you're going off of in the lab. because you can, make this guess and write it out what you think it is, but then you have to go look at the NMR, does it match? Other questions?
There's a chart on page 1015, figure 2645, it's also in our notes, of the low delta, high spin, and then increasing delta, and then high delta, low spin. And that's how I arrived at 0 is because carbon monoxide is at high delta, low spin.
Exactly.
Is that an okay way to determine that also?
Yeah, so that's all you had to look for. So yeah, you could look at the spectrochemical series, which was like, yeah, what I was looking for. I think I gave full points for that answer of like, yes, I recognize this is a high field ligand, so it's probably going to be a low spin complex. But yeah, that was kind of like a lot. So it's excellent that if you got that, but I also wanted to be generous, for everyone. Since this is kind of a lot, and it is a higher level concept, like looking at all this. Like this is, inorganic research essentially is what they would do. You make up your diagram based off of the geometry, right? You get your crystal structure that tells you what shape it is. You draw out your little lines. You draw out your possibilities. You get the data, and then does it match? Does it not match? So I apologize for the oops. But you guys handled it really well, actually, so I was pretty pleased with y'all. All right, other questions, comments? This is our last week of class, so it's scary. No lab final. Yeah. Yeah, so we're still doing a lab, so on that note, just a reminder, this is a fun lab, the aspirin synthesis. And I do have it printed out for y'all, so don't miss it. We'll be making aspirin, although I don't recommend you take your aspirin, but I wouldn't do it because of purity concerns. Yeah. On the last quiz, yeah. On the which one has cis and trans isomers. So that one I noticed. The other most selected answer was probably A. And so I'll kind of draw that out. So cobalt. And so the problem with A and I'm kind of simplifying it. So there's A, except what are these isomers called? They have other names. Yeah, FAC and MERS. So these are not just cis or trans, right? So they have the name, so this would be FAC. And their other name, at least in the textbook, right, was cis-cis. But that doesn't match with cis. So just with the cis and trans isomers, it's only 2 different groups. And so if you give me a second, I'll draw the difference out. So right now I'm just drawing the MER isomer, and so that's the cis-trans, but I still use those terms. Oops, sorry, I'll just put a ball here. So that's A, but yeah, those are different isomers versus the correct answer of C, where you just had 2 different chlorines. So you could get cobalt, and they're either across with your waters in the middle. So there's your trans isomer for that one. And then cis. So that's the difference, just that that second formula, C, has still 6 things coordinated to it, but now just 2 chlorines. And of course, that other chlorine is outer sphere, so it doesn't matter. Only for charge balancing purposes. Does that make sense for 3 now? Yeah, so it just goes back to the naming formalities. So these are just cis and trans. Well, these are cis-cis or cis-trans, but again, I would use these terms of FAC and MER just because that's what's more commonly used. Other questions on quiz, homework, anything else? Or last minute announcements? I forgot when I said the deadline was for your papers for bonus points. Monday, okay.
Do you want us to submit that, like, over email?
I guess if it's a Monday, email, yeah, for your bonus points. It's either email or hard copy. So yeah, Monday.
If we do hard copy, can we still turn it Tuesday for the bonus?
Yeah, I'll allow that since I like paper copies. So yeah, I'll just put it Tuesday then. So next Tuesday is our hard deadline for +5 points. And then of course you have until the end of the quarter, which I forget when grades are due. I think the quarter ends officially on Friday though, right?
The grades are posted the 22nd.
I'm glad you know. I don't.
I just saw it. There's a bathroom thing in there. I was using the bathroom. I was like, oh.
Are those the toilet tissues?
Oh, yeah.
Nice, okay. We know those are working now. Any other questions, comments? So yeah, this will be our last week of lab, so don't forget your pants on Thursday. No lab the final week. We're not doing lab practicum this year. So hopefully that's okay with y'all. All right, anything else we need to address before we dive into polymers? All right, so let's look at polymers. Again, these are our hodgepodge chapters. Try to keep it general. So what's a polymer? I'm sure y'all know what polymers are. Somebody tell me some example. Probably. I'm pretty sure latex is a polymer. So what is a polymer? What did you say, stuff together? Yeah, so that's a basic concept, right? So repeated addition of small molecules. So just people often use like the train car analogy. So you have your monomer as your little single car, and then obviously the train ends up being your polymer. But then, right, there's all sorts of polymers. So DNA would be considered like a naturally occurring polymer. So it's made up of all the different components of DNA, which we'll look at, uracil and the other amino acids. So that forms DNA, so that's naturally occurring. Or synthetic ones. I'm actually not sure if latex is a polymer. I'm not sure it is. It's like an emulsion, apparently, officially. I know it's, I wonder if neoprene, though. Neoprene might be a polymer. Oh, we gotta look it up. anyways, nylon's a polymer. Yeah, neoprene is a polymer. So a lot of what kind of substances tend to be polymers? Thinking like a big, large, broad category. Fossil fuels, yes, or so fossil fuels, which ends up being your plastics. I'll kind of put those two together. But yes, those are the big component, right? Obviously, you're making plastic, so we'll look at all that. So jumping ahead, right? Most plastics are polyethylene, and those are super abundant, so a lot of fossil fuel goes into that. We'll go back to this section. And so here's just another kind of cartoon, simple explanation of polymers. So there's, again, our monomer, just represented. And then you link them together by some sort of chemical linkage, and you get your polymer. And so most polymerization reactions occur through a radical mechanism. And so here's just kind of a preview of what this would look like. So you have your radical initiator, and then that's going to break the double bond. Then you have your another radical, so that goes on to react with another equivalent of your monomer, and so on and so forth. And so this goes into a whole other branch of chemistry, so polymer chemistry, and how you can kind of control those conditions. And so that's all polymer chemistry is like how long can we make these polymers, how consistent can we make them? Because of course when you do a reaction of this sort of polymerization, you're going to analyze it, see how long your fibers are, and see how well you can kind of control that. So that's where the tricky part comes in. And so then this is terminated when you have the reaction of two radicals when their ends meet, so these would meet and then end your polymerization. So again, that's something you could try to control with concentration or any other additives, how you do the reaction. So trying to control that termination so you can control the length of your polymer. So Teflon is, of course, another polymer used for coating, but personally I don't recommend Teflon. All these things are nasty. But this is the monomer, and again, you can see how you break the double bond, and then it gets broken and made into that polymer chain, so making your carbon bonds. And so notice, right, you just have this N here, and this is just your repeating unit, so however long your chain was, that could be N equals 10 or N equals 200, whatever the reaction conditions are. And then you just specify N, and obviously that repeats. So now looking, and this is from your book, and this is just a nice chart because it lays out everything. And so again, polyethylene is probably the most common, and it's in basically everything. So containers, shrink wrap. So that's going to be your number one recycling. And so polyethylene is also the easiest to recycle, so it's the most versatile. And so that's how it goes with the numbers too. So as you go down the numbers, they get increasingly more difficult to recycle, or maybe not even at all. And then you have polypropylene. So this is also super common. So notice it's made from propylene. So this little 3-carbon monomer here. And then again, break the double bond to form your chain. And so polypropylene, this is actually 5 on the recycling. So now this already is difficult to recycle. So that propylene, right, extra group. So now you have difficulties recycling it. But it's used in like molded plastics, labware, pipes, valves, so very prevalent, polypropylene. And so what else? So then this is PVC. And so obviously, right, there was that big spill recently with PVC, or really the monomer, right, the vinyl chloride. So that's a nice gas, and of course, if it spills, it reacts with the water in the atmosphere to make HCl, so obviously that's not good, but this synthesis is pretty well known and cheap, hence why they do it, hence why large amounts of vinyl chloride were traveling by train everywhere. So obviously, you're probably pretty familiar with PVC in building materials, right? You see it in pipes, tubing, electrical insulation, so obviously extremely prevalent. And so this is 3 in the recycling code, so it already gets difficult as well with that chloride group. And so here's neoprene. Speaking of neoprene, so this is kind of the alternative to nitrile. So this is supposed to be super like hypoallergenic, so nobody's supposed to be allergic to that, hopefully. And so it's from this chloroprene monomer. And so it's used in different hoses, and we'll also add in their gloves as our alternative to nitrile, since there are nitrile allergies. I don't think neoprene is on the recycling code. And then other polymers, so plexiglass is also a polymer, so made of this methacrylate. So helmet visors, aquariums, so that's super useful, right? Nice hard plastic that you can see through. Dentures, office furniture, artificial fingernails, so the list goes on. And again, you can see this double bond is broken and forms your carbon-carbon bond. And so there's Teflon. So there's the monomer, the tetrafluoroethylene, and so again, we know that's on nonstick coatings, which definitely recommend cast iron at this point. So yeah, I don't advocate any chemicals, definitely go cast iron, but that's what it's used for. And acrylonitrile, so this is used in acrylic fibers. So different awnings, materials, carpet, carbon fibers. And then our last one on at least this list is polystyrene. And so this became hugely popular, I think in the 80s probably. There was a polystyrene craze. I'm not sure. Let's look at when it was invented. But as you can probably guess with the code, and maybe what you know about styrofoam, it's pretty unrecyclable with this styrene, so that makes it pretty difficult to recycle. And so a lot of times it is just trashed, unfortunately. I'm trying to see when it was invented. I think it was invented in 35 apparently, but from my understanding of plastics manufacturing, it really took off in the 80s. It became prevalent everywhere. And of course now they're dialing back on styrofoam because it's so difficult to recycle, unfortunately. I know ours personally ends up in the landfill, so not good. Oh, we didn't. Where's the nylon? All right, so let's look at a general polymerization reaction. And so you might have to do like identifying what could make a polymer on your exam or something. And so what you're looking for is, so what's this group? What was that group called? So acetic acid, we've looked, is an example of this. What did you say, carboxylic? Yeah, so carboxylic acid. Right, so we're basically looking for that acidic proton. So just highlighting, right, that's your acidic proton. That's where the action is going to occur. You have action going on here. And, well, actually, it's going to be attacked, though, at the carbon, at these polymerization reactions. So this carbon wants to be attacked. And so that's what happens. And so we're going to be losing water. So let's highlight that. So we have water. And then you can see where we're going to be making the bond. And so basically what happens is you have this electrophilic attack. So, right, nitrogen has those lone pairs. Don't forget about that. And then it's going to go ahead and attack this carbon. So then it'll push initially those electrons up. And let me draw that kind of intermediate for a second. So carbon, then central carbon, oxygen, so that's pushed up. We have our OH there, new bond with our amine, and just kind of leave that as an R group. And then so what happens is as our double bond reforms, now our OH can act as a leaving group and probably pluck off a hydrogen as well in this mechanism to get us to our final product, so that we form water and then we make this bond here. And so on Thursday, at least my plan is to do a little nylon synthesis demo for you. But we can at least look at the chemistry on how it works. And so again, you're looking for that carboxylic acid group. You have your OH that can leave. And then these nitrogens, you can add them on either side. And so that's what happens. So now we have to look at it. So it's showing where it attaches. So this is, right, this chain, your hexane dioic acid or adipic acid. So that's this monomer, right? We lost our OH, and then we lost another H to make water. And then we made this bond where the nitrogen goes to that carbon, right, your double bonded carbon of your carboxylic acid. So there's your amide bond there, carbon, nitrogen. There's the rest of the 1,6-diamino hexane monomer. And then this would just repeat, obviously. And so this can add to the other side and then chain another acid to it and just on and on. Trying to highlight what goes where. So does that kind of make sense? Do we see that? How to put the pieces together? And so again, you make that essential amide bond between your nitrogen and your carbon. And so you can also have what are called copolymers. So that's polymers made from more than one type of monomer. So in this case, like polyester, you have your two different monomers. So this would be your alcohol. And then, of course, this is your carboxylic acid. And this is similar to your ester reaction. So this is called esterification. So that's when we had an alcohol plus a carboxylic acid. Let's take a look at that. So that was last week. If I can find it. So remember when we were looking at how to make these fun esters, and we have the same sort of reaction, so alcohol plus carboxylic acid, we had it attacking right our carbon there, so then we made our ester. Does that kind of sound familiar? And so same process is happening here, same mechanism. So same thing, right? Your alcohol, carboxylic acid. Instead of just making one ester, though, you can go ahead and make a huge polymer chain. And so what else can we call this reaction where we make water? What type of reaction is that? Yeah, dehydration, or what's the other name for it? It's more commonly used. Condensation. So condensation reaction, I'll put dehydration. Dehydration in parentheses. But right, basically you're losing water, so that's the big key to these reactions. And then just identifying groups. So this is, right, your ester group here now in your polymer. And so just notice that, right, carbon, double bond oxygen, and then to another oxygen, but instead of an H there to make it the carboxylic acid, it's bonded to any other R group, which makes it the ester. And so this is just kind of giving you a feel for the scale of all these reactions. Again, if people were actually concerned about climate change, which they're not, at least not in any ways that would be beneficial, then we would cut our plastic production. So you can see annual production in thousands of metric tons, and it's just really ginormous. So most of that being dominated again by the polyethylene, so all that thin-use, single-use plastic. A lot of it is, of course, in like packaging. I don't have to tell you, you order something from anywhere, your new phone, whatever, and it comes with like a billion wrappers on it. So that's where most of it's being going towards. And so you can just appreciate, of course, PVC is also up there, and then it kind of drops off. And so we can also have different reactions. So we can also have what's called these cross-link reactions. And this is where we start to get different structures or also kind of link different polymers together. And so one example of that is this. Have you ever heard of Olaplex? Yeah, the hair thing. Although some people were trying to tell me that maybe it's bad, but I don't know. But anyways, yeah, the hair thing. So exactly. So how it works, at least how it's supposed to work, is it repairs the damages in your hair by relinking these sulfide bonds. So just like that's shown here where you have this example, so you have your sulfides here, and then what happens is you make this disulfide bond, right, where those two sulfurs link. That's exactly what Olaplex does with your hair. So it like synthetically repairs it by repairing those disulfide bonds that were broken in your damaged hair, and it fixes them, or at least it's supposed to. I guess this.
My mom is a hair stylist. She like dyes and cuts hair and all that. She says it's really good for your hair.
So she likes it? Okay.
Yeah. It's really, really expensive though. So
Yeah.
She doesn't use it, but it's really good for like when you're dyeing the hair, putting it on the hair while you're dyeing the hair so it doesn't damage it as much.
Yeah, since it protects those disulfide bonds, exactly. So yeah, that's cool. So I'd love to hear more. The real world disulfide bond making. And so let's see. So if we continue looking at our chapter, so then we go into proteins. And so what are proteins basically? I have it there for you, but so they're a bunch of amino acids. So they're basically a bunch of polymers, right? And then we start cross-linking them, and then of course that gives them their different structures and shapes and all that. And so let's first look at a monomer. So again, just defining a protein. So biological protein is whoever has a monomer unit that is an amino acid. And you probably are at least somewhat familiar with the amino acids. I should have printed out a chart for you. I'll bring it for Thursday. So these are just all, I like this graph. It's just a picture of the 20 common amino acids here. So blah, blah, blah. So we'll kind of look at, they have, of course, these different naming codes. So we'll kind of look at that. So they have just a single letter code, which honestly, I don't really see the single letter code as much, but I'm also less of a biological chemist. But what we do see a lot are either these 3-letter abbreviations or their codon representations, which we'll look at what that is. And so most of them have a chiral center except for glycine, so this one just has a hydrogen attached to it, but otherwise they all have chirality. So let's look at this. Right, so this is a chiral center, so just refresher, chiral center has 4 different things attached to it, doesn't matter what those things are. And we've kind of touched upon it in here with the origin of life, I believe. But so most of life is L-based. And so we've mentioned this, so life all has a certain-handed chirality, and then oftentimes when you do like research, they work on the other enantiomer. So this would be like the D version. So you would make like artificial peptides using the different versions, so the D version. What's interesting though is I think there are allergies that can come up with people that work with these synthetic peptides, especially for long periods. Not entirely sure why. I don't know if it's something with the different handedness, but people can develop like allergies and sensitivities to these synthetic amino acids. So that's interesting. And so, let's see. Looking at peptide bond formation. So looking at it, what type of reaction is this again? Condensation. So another condensation reaction. So it should be a little theme going here for you guys. So again, you just want to identify what's going to be leaving. So in our peptide bond formation, we have our carboxylic acid again, and we have an amine. Our OH, our alcohol, is going to be acting as our leaving group again. You have that nitrogen with the lone pairs, so similar mechanism. It's going to attack that carbon, moving those electrons up, and then reform the double bond, and the OH goes away. And so once again, right, we have an amide bond formation. And so something that you want to be able to do is then be able to pair up how they would be synthesized. So let's say you're trying to make a peptide, and you want to make an alanine serine peptide. And so you want to be able to look at your amino acids and then figure out how and where they would attach. And so in this case, the way it's named, alanine serine, right? Alanine's going to go first, and then we're going to lose the OH of alanine, and then make our amide bond there with serine. So again, you're just making sure you connect it to the right carbon, so that nitrogen needs to go to our carboxylic acid carbon with that double bond. So that's something that we'll practice. And so in comparison, if you flip them, so if you had a serine alanine dipeptide, then if serine comes first, you're losing the OH from serine and making the amide bond there. And so that's a little tricky, right? So they both have carboxylic acid groups and amines to bond with. So you would just go kind of in order. And so this is just a general scheme, but you want to be able to, again, put it in order. So your carbon bonded to your carboxylic acid, make your amide bond. So just kind of identify these points, right? That, oh, okay, well, I had an amide bond form there, and then you could either backtrack it out, you know, write what the starting material was, or figure out how to make it. And then again, right, carbon, carbon, oh, here's your amide bond again. So there's your next unit. And so just kind of do that, right? Identify where your bonds are being made. All right, so let's look at these different, what they call levels of structure here. So the primary structure, so that your first level, is just your sequence of amino acids. And so this is just showing you how many amino acids are involved in all these different things. So insulin, that's relatively small. But then if you look at, you know, collagen, that's a lot larger with your amino acid. There's hemoglobin, so that's obviously a large complex structure. And then so your secondary structure is just the 3D form of local segments. And so there's a lot more secondary structures, but we're just focusing on either alpha helixes or beta sheets. I was just looking at a picture. There we go. So right, secondary structures, again, the alpha helix kind of goes in this curve structure versus beta sheets that are kind of more flattened structures, as you can kind of see. But again, that's just more general. And then once you get into the tertiary structure, so what that would be is now the full, right, 3D shape of the protein and how it is. And again, obviously, you know, that's going to be complicated, and you can look at all these structures, though. Different pictures. I was trying to find a picture of hemoglobin, but. And so this can be tricky, right, to get the 3D shape of the protein. And so it's pretty difficult to crystallize proteins to get the shape, but you can. And there's also, of course, all sorts of modeling that you can do. That's always a good area of research. So let's look at kind of DNA and RNA more. So nuclear nucleotides, these are just made out of a sugar phosphate group and a base. So there's DNA, RNA. And then, so you may be aware, so I think many of you have taken lots of bio courses. So of course, these are the 5 bases that occur in DNA and RNA. So adenine, guanine, cytosine, thymine, and uracil. And then of course, thymine is only found in DNA, and uracil is only found in RNA. All right, so now let's look at what our nucleotide is made out of. So we said it has a sugar phosphate group and a base. So we have, right, our phosphate group over here. There's our whole phosphate. And then of course, right, our sugar is in the center there. So sugars, they're usually represented by either this 5 or 6 membered ring, so depending on the sugar. And then of course, sugars have a bunch of alcohols or hydrogens on them, so we can identify our sugar. And then over here is our base. So whatever base it is. And so in this case, it looks like, right, adenine is conjugated here. And so that's our structure. And then of course we can just see this unit repeated. So phosphate, sugar, base. And then it would go on, right, phosphate, sugar, base. And then, so what's interesting about the double helix is, so what keeps it all together, and of course, so you're aware, it's often represented by that twisted ladder. So you kind of have, right, both sides of your base coming together. And then what's kind of fascinating, to me at least, so you have your bases here, and then what type of bond is this? Do you guys recognize that? This little through space. Think really simply, if you can. Yes, hydrogen bonds. So super simple. I don't know why. I find that super fascinating, really. That your double helix is just held together by hydrogen bonds. So right there's your hydrogen bonding. So you remember that interaction. And of course, the little lines indicate that that's just hydrogen bonding with those electrostatic interactions, so not a physical bond really being formed, just electrostatic interactions. So, right, recall back to hydrogen bonding. So, I don't know. I find that both scary and fascinating for some reason. And so in this case, so this is, right, adenine and, I forget my amino acids. Adenine and thymine, so A and T. So when these form together, they only make 2 hydrogen bonds. And you can, again, just kind of see that, how they match up together. That's all you're really looking at. Versus, so now we have C, G, and C there. So that's guanine and cytosine. And so when these get together, now they're held together by 3 hydrogen bonds. And so other tricks, so you probably have learned this in the past, but notice, right, A and T always pair together. And again, they have to match because they only have 2 sites each for hydrogen bonding. So that's why they're always used. And of course, people use the trick of, oh, they're both kind of straight looking, all lines, so they go together. And then, right, C and G are both kind of curvy looking, so they go together. And don't forget about U. So U goes with A and T, which is just kind of awkward. And just remember, right, that's with RNA. And so again, C and G, the curlies have to go together because they both have 3 sites then for that hydrogen bonding interaction. And so you could just now appreciate this. So looking at this structure, so A and T, again, hydrogen bonding. Now C and G, 3 hydrogen bonds there. Back to A and T with 2 hydrogen bonds, and then back C and G, 3 hydrogen bonds. So it's on my next page. Okay, let's go back. And so now let's look at, so how do we code? Well, actually, where's my code page? This will be better here. So now how do we code for different amino acids? And so for DNA, so going from 5 prime, so let's just say this is our sequence, so A, C, C, T, C, G, A, G, 3 prime. And then when we match it up, now it goes 3 prime, and then you have to, of course, take the complementary ones, so A with T, C with G, so T, G, G, and T goes with A again. And then this is DNA, so no U's in this one. So then C with G, G with C, T, C. And so then when you rewrite it, right, you start with the 5 prime, and then so that's C, T, C, G, A, G, G, T, so just writing this backwards. And so now starting with 5 prime, we can look at each of these 3. So now every 3 makes up an amino acid or some sort of stop or start codon signal. And so in this case, you start with your 5 prime and then CTC. So now C, except there's no, on this chart, since it's for RNA, instead of U here, this would be T. But CTC, so then that matches up with leucine here. Or if you prefer, so I think this is a DNA one specifically. So again, CTC, so see how that matches up with leucine there. And then GAG, so start in the center, GAG, and I think I misread that. And then GAG would be alanine, I think. No, glucine. I can't read these. Oh yeah, GAG. Sorry, I can't read these tiny. Questions about this? You probably have seen this before, I assume, in other classes. All right, let's look at starches, and then we'll still have to do some practice of putting amino acids together. So now, starches, can anybody guess what this is a polymer of? You could probably guess by looking at these in the notes. Yeah, so they're polymers of sugars. And so we have our sugars here. And so once again, doing a polymerization reaction, adding these two polymers together, and you could probably guess, looking at these two, what's going to be happening. So you have your oxygen here. This is now what's called nucleophilic, so it's going to go towards this carbon. Carbon's electrophilic. It wants those electrons. So that's where that bond's going to be formed. And once again, this is a condensation reaction. So a bit of a theme here, right? So every time we put stuff together, it's a condensation reaction, so making water. And so there we have our structure now. So glucose and fructose, two simple monomers of sugar to make sucrose now. And so you can appreciate, so this, at least basic ring here, is just like cyclohexane, essentially, so kind of with that boat and chair conformation, so that's why it's drawn all funky. And so we also have what's called alpha and beta forms of sugar. And so all that's looking at is these two hydroxides and seeing whether they're both, so this is down and down, so they're both down, or they call it the same side, but you're kind of looking at what angle they're going at. So if they're both down, this is called the alpha form. So you also see alpha. And then versus a beta, and so beta, right, this one's going down, and this one's going up, and so now they're on opposite sides. So now this would be beta. And so a lot of times people use this terminology when linking them up, so determining whether it's an alpha or beta connection. And again, that's just what direction. So this one, they're both down, so this would be, right, an alpha connection here. So that's all that refers to, is again just chemistry, or stereochemistry and orientation of this OH group there. Let's see, what else do we have? Blah, blah, blah. So let's look at, I'm going to give y'all a practice problem. So go ahead and see if you can draw out what this chain would look like, this peptide chain. So if I give you glycine, met, phenyl, so you have to look at what those structures mean. But see if you can draw those connections, right? So you're thinking of your amide bonds. Where is it going to bond? You're going in this order. And then I'm just going to run to the bathroom, but I'll be right back. And I just pulled up the amino acid sheet. How are our pictures going? Oops. Oops, I drew mine a little wonky. Did we get something that kind of looked like that? So I care less about like what it looks like with the sticks. What I care about is you have the right number of carbons and all the atoms, and then of course your bonds. So we have, so this is, right, glycine, except we took off the OH. We can go back and forth. So, right, glycine, we connected it with methionine. So we have to, of course, do that connection. And the trickiest part is just connecting it right to the nitrogen. So it's a little funny. So then it goes on this one, so the nitrogen hooks up to that carbon. The sulfur is just hanging out then. So I have mine just drawn like so. So remember, it's always an amide bond formation. So you're always looking for that carbon nitrogen where they link up. So let's see. Hang on, I need another reference sheet. As you can tell, I don't know my amino acids. I never took biochem, so I never had to memorize them. That's all I ever hear about biochem is, oh, I had to memorize all of the amino acids and the Krebs cycle and all sorts of other horrible things. Oh, man. Okay, there we go, finally, some sheet. Internet's being kind of slow. All right, apparently it's never gonna load. Yeah, what I was trying to emphasize, so if we redraw methionine here, that's why I wanted a reference. Don't screw it up. So there's your amine that it attaches to. When you're making that linkage, you have to attach it to that nitrogen. And so that's why I kind of drew it, I don't know, more skeletal, and so that you could just see where it's bonding to. And then I showed, right, the CH, the two carbons, your S. And, you know, if you want to draw it pretty, that's fine. But I was just trying to get the right number of carbons in there. Then there's your carboxylic acid from methionine. So kind of block off right where met is here. And then of course, right, it lost its alcohol group, then attached to our next one. So phenylalanine, again attaching at the nitrogen. So that's why it looks, I feel like it looks funny when I draw it. So nitrogen attaching to your carbon. Trying to do. There we go. Only took forever to load. So right, just so you can follow along. So phenylalanine, so we hooked it there. So nitrogen from our previous one, so methionine goes to our phenylalanine here. So nitrogen, there's a carbon, that carbon, phenyl group, and then the rest of phenylalanine, so right, the carbon there, nitrogen, and then our last one, so glycine. See if I can find glycine now. There it is. And so ending with glycine, so again attaching at the nitrogen, so carbon, nitrogen, and then the rest of glycine finished off there. Again, 1, 2 carbons, so 1, 2, and carboxylic acid. Does that make sense to people? Do we feel okay about that? Kind of identifying amino acids. So that'd be like another question too is, what if I gave you a structure? Like, could you backtrack what the amino acids are, you know, just based off of the structure? Of course, obviously having a reference, but. All right, I think we're about out of time here. So the plan for Thursday is hopefully do nylon demo, and then otherwise we'll just be doing more like practice, so getting a better feel of questions and answering them and predicting product type scenarios, and also going back and looking at like our other organic reactions probably, so you feel like comfortable about that and kind of what you need to know for your exam. All right, we'll end there. So I'll see y'all on Thursday for lab. So don't forget pants and shoes on Thursday, and I have homework and lab printouts if you so desire. Then I'll hang around on stream for another minute or so if there's questions. Otherwise, I will see y'all on Thursday.
Have a good day.
You too. See, I have quizzes. Tyra. I think everybody else got their stuff. All right, thanks again, chat. I will see y'all in person on Thursday.